Thank you. I'm very glad to be among the speakers in this conference. Thank you for the invitation. So today I will be talking about the retrieval augmented generation on the code-related task. I'm working at JetBrains Research, where we're doing research on various deep learning, AI, and machine learning on related to code. So let's start from the beginning. When you're, most of you are, I think, using various kind of code assistants. It could be kind of Cursor, the fully assistant, GitHub Copilot, or maybe you're using agents. Maybe you know Juni from our company, or JetBrains AI assistant, or you're using just a completion. When you're using all these tools somehow should know about the state of your repository to make much more relevant suggestions or answers to your questions. And the question is, what is the best way to provide your repository to this model? Okay, one of the obvious ways is just to put the whole repository into the context, but there are plenty of problems with that approach, because you can, first of all, your repository could be too large for the context. Second, it could be too many distracting items and instances in your context, which is not relevant to the question, and it would degrade the performance. So this work have started when our production team asked us to investigate the best ways to input the context about your repository, so your code assistant or code completion could better understand what you really want. Following this goal, we try to find the best similarity metrics between the query, your question or completion, and the answer or completion. As well as we try to explore context size dependence, because especially in code completion, you're strictly limited. You have strictly limited resources to complete fast, because user cannot wait for several seconds or 10 seconds until something will be completed. In agentic stuff or assistant, you obviously can wait longer, and you can use much heavy machinery. Yeah. So let's begin. To benchmark the retrieval, we use two tasks that mimic real-world scenario. The first task was code completion. So giving the repository state, the task is just to complete one line of the repository. So we used the code completion database. Kudos to Zhenya Glukhov, who gathered this data set. He's sitting here today. The main languages were Python and Kotlin. Metric was exact match. There were about 2,000 data points for each language. The another task was the bug localization task. So which means that given an issue, the model should select most relevant files to this issue and rank them somehow. The number of data points in this data set was very small, about 50 for each language. More details about these tasks and data sets you can find in our paper, which we called Lone Code Arena. Let me speak a little bit about how the tasks are formulated. The code completion task. In code completion task, you have lines in your files, which you have a target line, which is the ground truth, and the task of the model to generate this target line conditioned to some completion prefix. Completion prefix could be the whole file or part of the file just before the completion, before the ground truth. And as a retrieval base, you have the whole repository. It could be either files or chunk of files, any way you want. And the retrieval task is to, given the completion prefix, you should retrieve from the database the proper context, rank them, and just stack into the context. Then generate the line and to check whether this line matches the ground truth. So in back localization, the task is a bit more, I would say the formulation of the task is much simpler. You have a repository with multiple files. You have issue description in natural language, but it can contain some code. Then the retrieval task is to rank the files in the repository according to the proximity to this issue description, and then the ranked files are passed to metric calculation. We used NDCG metric, which is just a metric of how well the files are ranked. So what retrieval approaches you can use? The first and the simplest one, just put everything which is in the same directory, and if you have place, put anything more which is close to it. This we call path distance composer. It scores the files just according to the distance, the path distance between files. But the main thing I will speak today is chunking and scoring. You can chunk your files into some chunks, and then score the similarity of the prefix or the issue, and use these chunks to create the context. Also, we explored repo structure where approaches, which uses data flow graphs or structure of imports to deduce the closeness of the files. So let me dig a little bit deeper into the how chunking, how our retrieval composers work. It contains three main things. First, the chunker, the way how you split the files. You can keep them intact, the whole files. You can split them by lines, for example, or you can split it into syntax-aware things, let's say by classes, by methods, or something like that. Then you need to score. These chunks, this proximity of these chunks to the your prefix or query. And the splitter is a technical thing because during the scoring, you should split the chunks into some kind of tokens. It could be tokens, words, or even lines of codes to calculate the proximity of chunk to the query. As I've said, you can use full file, you can split into the fixed lines, or you can use some syntax-aware chunking. The splitter, for the splitter, you can split your chunks into as BB tokens for lines or for whole words. And then after that, you would like to score the chunks and the completion and your query. We benchmarked three types of scores. First, the simplest one is intersection of union. That is just a ratio of common tokens or words or lines of codes between your query and the chunks or the files. The another one is BM25 score, which is quite the similar thing, but much more complex and much more stable for the for the practical applications. It also scores the intersection between the instances in the query and the document and the chunk, but it does it much more in complex way. Yeah, and also we used dense embedders, so you can map your chunk using the LLM. You can map into some vector, and then just calculate the distance between these vector, and the closer vector are, the closer your query to the. We use two dense models. The one is in float E5 large, and the second one the Voyager 3 family. That is proprietary model, so we use it via API. So you have a whole bunch of these hyperparameters and design decision you should to make. So our goal was to select the best combination of these options. Let's move to the results. So these results depict the exact match versus the context length, because we wanted to benchmark the quality of the generation on the various context budgets. And you can see here that BM25 dominates in accuracy across two other options, which is intersection of union and dense scorer, which leverages the embeddings of the files of the chunks. Somehow, what was surprising that for code completion task, the dense encoder, at least the E5 dense encoder, was pretty had the worst performance here. And another surprising thing was that intersection of union over the line splitter, so intersection between the line existing in the model, it was pretty good too. You can see it works almost on par with BM25. And another important thing is the latency. We found that there is no need to split your chunks of files into the BPA tokens. If you're using BM25 or intersection of union, you can just make a word splitting. By word, I mean just spaces. So then we benchmarked the chunk sizes. We tried to use different sizes of chunks. Sorry for the presentation. I should have used logarithmic scale, and the results can be hardly seen here. But what we observed is that the optimal chunk size depends on the context size. So if you have smaller context, like say less than 4,000, you can use smaller chunk size, something between 32 and 64 lines. But the smaller chunks, from 8 to 16, works much worse. For longer context, okay, more than 8,000, you would prefer to use larger chunks or even whole files. And we also benchmarked the line splitting with syntax-aware chunker, and we found that it worked on par with syntax-aware. So there's no really difference in that. So that means probably you would, in this task, you would prefer more simple and more fast approach. Also, we benchmarked three different retrievers. The first one BM25, which I spoke before. The Draco is the repo structure where retriever, which is aware of the data flow graph and AST, and the pass distance is our baseline method. First of all, you see the BM25, it almost beats all other approaches. here. So there is no actually need to make very complex design choices. You can just put everything to BM225. And path distance is a very poor metric. However, if you have a very large context, path distance results became closer to other retrieval, but probably just due to the fact that you've put almost all relevant stuff into your context. Yeah. So, what is the outcomes from this part? First of all, the BM225 on words outperforms all other setup that we have tested. For shorter contexts, I would suggest using intersectional union on the lines for completion task because it's very fast and the scores are pretty good too. And there is no need in token splitter that will save your compute. As for the chunker, adjust the chunk sizes to the context. The smaller context, probably you need smaller chunks. For a longer context, you will need the larger chunks. There is no need in complex syntax-based chunking. And the last one, at least for this task, do not need to include non-code files. That saved us plenty of compute. But probably it's due to the task. It is due to the task nature because the main benefit was from the code that resembles some similarity with the target prefix. The next task was the bug localization. And we also benchmarked sparse metrics like BM25 and intersection of a union. And here, just to recall, the bug localization is more natural language to program language retrieval. So you have your queries in natural language, and you have to retrieve program language context. So in this case, BM25 bits far bits intersectional union. That's understandable because it understands a bit more about your context than a simple intersection of the words. And the splitter performance is approximately equal, so you would prefer word splitting over the BP tokens. And then we benchmarked the dense approaches. And here we see the whole strength of the really large dense encoders. The Voyager family, which is proprietary models, they beat pretty far the BM25 approach. However, if you switch to the open models, the local models, not large, they have 1 billion, you see that their scores are pretty close to BM25. So unless you have, I would say, one more, and we have a time. Time here, you see the BM25 is very, very fast. While Voyager has very, very large latency, but we have to say that we included indexing into these times, into these latency too. And even the more moderate encoder, dense encoder, it takes about 40 times more, 40 times longer response for it with approximately the same accuracy. So if you need if you are interested in precise results, you probably would like to switch to the large or proprietary models, but it will come with the cost of the money and the higher latency. But I would say if you pre-index your repository, latency should be slower, but it wouldn't work for completion at all, I think, because the latency still would be high. So the outcomes, I already said, the Voyager 3 code is the best performing embedder across tested We tested only 6 models, I would say. But proprietary models' latency is high. The longer context is not necessarily better. Yeah, probably I already covered all this, all other items. So another interesting thing is the latency for completion task on the dense and sparse approaches. First of all, you should know that for large context, which is 16K, the variance between the scores is pretty low. So the lowest score is 0.51, the highest 60. And I would say that if you are using long context, probably you would look more into the latency, not into the scores. And in this case, even path distance worked pretty fine. However, if you are interested in smaller context, which is probably our case, because for completion, especially a single line completion, you need very fast models which cannot afford very large context. Okay, usual context could be 1,000 tokens or something around that. So you should look into the scores more thoroughly. And here BM25 outperforms everything. However, if you are very interested in the very low latency, probably you would look into intersection of union across lines too, because it is pretty bad, but not so bad as path distance. So, as a conclusion, I would say first, sparse versus dense. The task type matters. If your task is program language to program language retrieval, probably you would expect the sparse approaches like BM25 or intersection over union would work the best for you, and it would take much less time for that and less cost. But if your task is some kind of natural language to program language, or you have plenty of time, like an assistant or an agent, you should look into the embedders and probably larger embedders, because E5 large, which is 500 million model, didn't work good for us. And I would say that you need really large models. I mean, by really large, larger than 500 million, to surpass BM25, even on natural language, programming language tasks like back localization. Proprietary models, latency is high, but it could be less significant if you are using, if you're pre-indexing. As for chunking, shorter context, shorter chunk size, simple rule. No need in overcomplicated and syntax-based chunking, and no need to include non-code files, at least on code completion tasks. So finally, our recommendations is first, make retrieval strategy to your tasks, then align to the chunk granularity. Consider efficiency, because there is always room for improvement, but you should be aware about the trade-offs of the latency and the scores. Complexity does not necessarily improve quality, so first of all, I would suggest to look into the simplest methods, not the complex one. And I would suggest to optimize and try a retrieval pipeline, because effective RAG system, they combine multiple strategies, and you need to tailor to the task your approaches. Yeah, that's all. Yeah, and I have to say credits to Olga Kolomitsova, who has done much of this work while she was intern in our lab. The paper could be found here. It's on Google Drive because we submitted it to the conference and we cannot post it on the archive for now. Thank you so much.
Thank you so much for the talk. That was very interesting. I think we have a few minutes to do some Q&A. Does anybody have any questions? Yeah? So if you can keep the mic a bit closer.
I'm sorry. Okay.
Thank you for a great talk. Can you go back to results for the retrievers on bugs task, issues task?
I think this one.
Yes. How you can explain this difference in Voyager chunking, that the shortest chunk is the best quality?
Yeah, that was a tricky thing. It occurred that the first, the imports that help a lot to the bug localization, probably due to the instances you import, they should match the query, and that was the thing.
Yeah, thanks for the presentation. Actually, my question related to the choosing the chunk size. So some programming languages are more verbose comparing to others. So it's the same chunk size for all programming languages. It's for more bug localization, I guess. And the second is still related. The second question is like, do you considering like some coder metrics like average method size or related methods to chunk together, like for better results? Probably it works or no. Just to choose chunk size based on some predefined. I mean, you calculate like average code size, method size, and etc.
Yeah. As for the first question, the dependence of the on the programming languages, for code completion, we use chunking for code completion. We benchmarked only Python and Kotlin. We have Java in bug localization, so we didn't find any strong differences. So I presented here on the only scores on Python, but for all other, it was quite the same. And the second question
is like to consider some code metrics like average method size or related classes to chunk together? Or
as I've said, we've tried some syntax-aware splitting, like splitting by classes, then by methods, and to fit the chunk size, and it didn't improve the metrics. So the line splitting was pretty good, probably due to the chunk size, because as you see, 32 lines, it's a pretty large chunk actually. 32 and 64 lines, it can encompass not large but decent, some medium or small method. So that was not the problem.
Okay, and another question. So are you indexing the project or the module, like indexing dependencies for faster like bug localization answer, or more correct or more accurate answer to the, like, say, bug localization task?
Okay, for more fair comparison, we haven't pre-indexed the repository. All the latencies was showed as the index, but obviously in production, the repository would be indexed and re-indexed once every some time when you change the repository.
And indexed stored in locally and.
Yeah.
Okay.
Yeah.
Okay. Thanks.
It's very costly to move it. It doesn't take too much memory, and it would be very, very high latency to take them from the cloud. I'm sorry. So thank you for attention.
Yeah, any other questions? Or?
Hi. Is this working? Hello. Yeah. Thank you for the great talk. Can you tell us a bit about your data set? Did you collect your data set? And if yes, how did you do that?
Our data set is published in Long Code Arena paper, this one. It contains, sorry, I should go here. The data set is Long Code Arena data set, which is published and there on Hugging Face. I didn't put the link, but you can find it in the paper. It contains six data set for benchmarking of the models, LLMs, on the large context of the repositories. So we use the code completion and bug localization task. Yeah.
So you created this data set?
I created only part of this data set. There is six data sets inside this work, and this data set was created by Evgeny Glukhov, not me, and this also not mine work. Mine was more CI build repair. It was much more difficult task for the model to. The model is provided the logs of the failed CI build on GitHub, and it should, on its own, fix the issues. So it's pretty much harder task.
Yeah, and the current models are not working well on those tasks?
Sorry?
The current models, are they performing well on those tasks?
On these tasks, they are pretty good. But as you've seen, the score for larger models about 70%, 60 or 70%. In a smaller model, is 50, 60. This one I cannot recall. You've seen the NDCG is about 0.7. But on CI build repair, no, it's about 10%, I think. But open hands run the agents, and they, I think, got about 40% in agentic setup, obviously. You should use agentic setup for such kind of task.